These are now showing up on Blackboard, if you've taken a look. All right, we're going to delve into equilibria. And there's two things to do while the topic is still simple. That is to look at KSP a little bit closer and to look at probably weak acid equilibria a little bit closer. And then things will get more complicated. In terms of the precipitations, it's still relatively straightforward when we say there are two things in solution. Can I separate them? Because as long as the differences in KSPs are really big, and there's a really big range in KSPs. But when we start saying, I have a polyprotic acid, and it has two components in solution, where are we? Then we have multiple things to consider. So we, like on the board from the last time, what if our acid is this one, and it splits apart in two goes, right? And the first one is dominance, and the second one is only minor. But what if? What if we find ourselves at a pH that puts us that this one has gone to its conclusion, and this one is kicking in now? How much of each of these things do I have in solution? Okay, that's complicated. That'll be next. So we'll build to that by doing a few things of, even though that's complicated, it is within bounds that there are only four things that could possibly be in solution, right? And so if I know the concentration of one of them, then I could figure out what the other one is. Okay. We'll get there. We'll get there eventually. Let's go look at some precipitations. We'd finished with a question that said something, right? Do I want to revisit that one now? We'll come back to it. Did we do lead iodide, mercury iodide? No, we just said if there's KSPs, one's going to precipitate first. But did we actually do a calculation on that?
We did for copper hydroxide.
Yeah.
Oh, we had iron, cobalt, not copper.
Okay. And what type of calculation did we do there?
We were looking for the concentration of OH.
Okay, that made one thing precipitate. Okay, we'll come back to that because we'll do it again with both and then ask, is there anything else that's missing? Okay, what I wanted to do is tie a precipitation curve to a titration curve that you already know. Okay, so we've done titration curves. We did them in chemistry too. We talked about them the other day. Everything you know, though, has been based on acids and bases. And the titration curve looks either like that. If you, what goes on this scale?
The pH.
pH. And what goes on that scale is volume of added Well, what am I doing? Am I adding acid to base or base to acid? I'm adding acid to base because if this is pH, then these are high values and those are low values, which means this is acidic, that is basic. All right, so there are a couple of regions on a titration curve. And what we would do in this particular case is you would have a solution. We put them in Erlenmeyers so that you can pick them up and swirl them. The glassware is built for the purpose. It has a narrow neck so that it doesn't splash outwards. And it has sides that are conical so that when things do splash, they come back down and we don't lose volume. That's what the Erlenmeyer is for. So, what would go in here if I'm adding acid to base would be a known volume of known concentration of base. And as far as we're concerned, acids put H plus into solution, bases take H plus out of solution, and the thing that takes H plus out of solution is hydroxide. Even if it's not a hydroxide, that's how I'm representing it right now. So, if I know its volume and I know its concentration, knowing that molarity is moles over liters, and there's my concentration, which is known, and there's my volume, which is known. I know the number of moles in that flask. The moles is molarity multiplied by liters. So all I'd have to do is make sure that that volume is written in liters, not in milliliters, because my concentration is in moles per liter. And then we would take a burette and we would titre in a volume of acid. Okay, do I know the volume and the concentration of the acid?
You will eventually know volume of acid, but not necessarily. But you don't know the concentration.
Yeah. If I knew the concentration and volume of the acid, why am I even bothering doing this? Is not an experiment. I'm not finding anything new, because this is an M times a V. And we're looking for that special point where the moles of acid is equal to the moles of base, where M1 V1 equals M2 V2. And that happens at a special place called equivalence. Where the moles of acid is equal to the moles of base. Okay? So what we would do is this would probably be unknown concentration of H plus. But the whole point of doing the exercise is to find the concentration of the acid, and we would do that by measuring out a volume into here until I reach the equivalence point. Now, we'll do this in lab for next week and have this be an exercise. How do you know where the equivalence point is?
You can either look at the graph.
What graph? Graph?
You can hook
I've got a clamp and a stand and a burette and an Erlenmeyer.
Do we have a pH meter? Is it a color? We can look for, or we
If
can
you have a pH meter,
Okay, I was thinking if we have a
fancy
pH meter.
over here with the pH meter.
Okay, sorry.
Yeah, if you had a pH meter, then you could measure pH. Oh, by the way, so we're about to start holding you accountable for this. How do you spell pH?
Wait, like, what? Lowercase p, uppercase.
Lowercase p, uppercase h is a beginning, but it's not the correct answer.
What?
It is lowercase p in italics.
Oh.
H.
The H is italics?
No.
Okay. The P is italics.
Yes.
So how would you write it?
Yeah,
Like that.
that's italics? I'm like, how, I can't write italics.
Yeah.
Dr. McGuire, that's
It's
cold.
the same thing.
That's cold. Okay, well then I'll do that.
Only when you venture into the world of publishing will people go, that's not right.
Oh. Okay.
So you have to write it twice?
No, you're trying to get his
No.
italics right.
Lowercase p, uppercase h.
But since we don't have a pH meter.
Yeah, well, if you have a pH meter, then you can measure the pH at known increments of added volume. So I would say this is an increment of added volume that I want to measure, and I would measure the pH at those points. And a hand-drawn graph, we did hand-drawn graphs, that you put a very sharp pencil through, or your computer does it for you now. These equal small increments have a name. What are they called? So if you're doing this by hand, even though we have the automation of pH probe, you'd say maybe every half milliliter of added acid, I'll pause and measure the pH. And what happens is the change in pH versus the change in volume here is so small, so big for such a small change, that if you were still doing it at this interval, there's a very good chance you miss these data points altogether. Which is why you really need to slow down close to the equivalence, and we'll spot that when it starts to turn here. Okay. In the absence of a pH meter,
We had, what are they called? Like, they change colors based on the.
Yeah.
The pH meter.
pH paper is an example of an indicator. Now what happens with the indicators, and this is what we'll do in lab, is, so what we'll do for the equivalence is we'll take an unknown concentration and measure a volume until M1V1 equals M2V2. And what we're going to measure is called an end point. I should probably write somewhere else. End point. And the end point is not equal to the equivalence point. If you have a pH meter, we can get really, really close to the equivalence point by plotting. So first of all, the human brain is really good at spotting inflections. So if you've got a sharp pencil, you could say that my inflection point is here. But if you plot the first derivative, which would be d pH over d volume, we get, it was curving that way, now it's curving this way. I get my turning point where my equivalence is, and if I take the second differential, I get that one, and where it crosses the midline, that's my turning point, that's my equivalence. But the end points that we see in a traditional titration is not the equivalence point. It's not. What we need to do is get it close to. So the end point is, there is a visible physical change. For most acid-base reactions, that's a color change. It's a color change of the indicator. What we'll do next week in lab is give you some strong acids and some strong bases and some weak acids and weak bases, and show you some, we'll pull all the indicators out of the back room, because there's a lot of them. And they all change color at different pHs. And if you select the wrong tool for the job, you get the wrong answer. So you need to select an acid-base indicator that matches the experiment that you're working on. I'm not going to bother doing that today because we're going to do that in lab. Okay, the equivalence point is the point where the not concentration, where the moles of acid is equal to the moles of base. Now they're both in the same flask, so they're both in the same volume, so their concentrations are the same, but the definition is the moles of this is equal to the moles of that, even if the concentration is also equivalent. The definition is that it's the mole amounts that are the same. Okay? All right. Now, this all gets a little bit muddy once we get out of chemistry 2 and that titrations are for acids and bases, because titrations can be for anything. There's no limitation that they have to be acids and bases. What if, I'll put that curve back up again, and we'll look, because there's a couple of regions that we want to look at. Is pH, and this is volume of added acid. Because I'm starting high and going low. If I was adding base to acid, the curve would go the other way. Okay? So, first off, equivalence happens at the steepest part of this curve, at the inflection, which we can spot by taking the derivative. And here, I'm going to call it concentration. And organic again. General chemistry, we write the negative on the other side. Organic, of course, we know that that negative does not belong to the hydrogen, it belongs to the oxygen. Okay. Equivalence is the second thing that happens on this curve. The first thing is up here. Here, the concentration of the base is larger than the concentration of the acid. Do you think anybody's ever said, stop there and tell me, how much acid have you got? Because when you add acid to base, it turns into water, right? So how much H plus is here? Ah, not much. Not much. Is there any?
Well, yes, because the pH got lower,
Yeah.
but
And water has this very small equilibrium where it auto-ionizes and makes H plus and hydroxide all on its own. So even when we're here and those two numbers are the same as each other, there's still some H plus in solution and there's still some hydroxide in solution, but they just cancel each other out. Okay. It is possible that somebody wants to know how much base is there? Right there. And how much acid is there? We'll be doing that. The general chemistry purpose of a titration is to find only that value.
yes.
Because that could only be the input, that could be the only possible answer. In quantitative analysis, people are going to ask, what if I give up halfway? How much have I got? So we'll be doing that. And then down here, now I have more acid than I have base. And it's a legitimate question when somebody says, if you overshoot the equivalence point just because you're sloppy, how wrong have you made your answer be? Because that's not much. In the world of added volume, that's not much. But look at what it did to the value of your pH. The fact that we're working on a log scale means that tiny little errors on the steep part of the curve can have really big impact. Okay? So we're going to come back and we're going to ask, what's going on there? So there's a couple of things that we want to know. One is what's happening before we get to equivalence. Then what happens when we get really close to equivalence? What happens at equivalence? And then what happens when we are past it? Because the end point that we've measured with a color change is not equivalence. We're going to do something you've not seen before. Everything that works for acids and bases in terms of titration curves, well, it's a universal truth. It works for other reactions too. Let's pick a reaction. I'm going to take some silver ions that are in solution, and I'm going to take some iodide ions that are in solution, and I'm going to make an insoluble silver iodide. Everything that we know about moles and molarity, titrations, and M1V1 equals M2V2 are still going to be true. It's just that the experiment is different. Here's what I would do. I would take an Erlenmeyer and I would put iodide. All right, a couple of questions. General chemistry 1 questions. How do I guarantee this silver gets to be in solution? It's currently in solution. I'm going to precipitate it and turn it into something that's insoluble. But how can I guarantee you right now, at the beginning of my reaction, that this is soluble? All something a soluble. And just make it be a nitrate. Silver nitrate. You can, if you look closely at all of the burettes stacked up in the lab, you can see the ones that have had the silver nitrate titrations running them, because out in the sun, the silver nitrate spontaneously starts to plate out of solution, and it will turn the inside of the glass purple. So grey purple color. So you can always see the burettes that have been used for nitrate, for silver titrations. And how would I make the iodide, which is going to be insoluble in a minute? How would I guarantee that that is soluble? All sodium salts are soluble. So this would be silver nitrate and sodium iodide. I'll put them together and they will make an insoluble precipitate. It has a pretty low KSP. I've got that written down somewhere. And it will precipitate. Okay. So I've got my iodide in here, and I would take a known volume and a known concentration of iodide. And then I would put the silver nitrate into a burette, and I'd know its concentration. And I would measure its volume. And when you drain out of this into there, it will make silver iodide, which will precipitate. And when you add a little bit of silver to the iodide, it precipitates. You add a little bit more, it precipitates a bit more. And when you add a bit more, it precipitates a bit more. And then all of a sudden, it doesn't precipitate anymore. Because at equivalence, the number of moles of silver gets to be equal to the number of moles of iodide. And what we would do, instead of putting a pH probe in there, all the pH probe is it's a fancy electrochemical probe. I put a silver specific probe in there and measure the silver concentration. Because what will happen is So up here at the beginning, the concentration of the iodide outstrips the concentration of the silver. And we'll look at the value, once the value of KSP goes on the board, you'll go, oh yeah, that won't stay in solution for very long. That's a kinetics description of an equilibrium problem. But the equilibrium is going to be very, very far to one side. Okay, so out here, we would expect that every single ion of silver that goes in gets snapped up by the excess iodide. It gets pulled out. And then there, at equivalence, those amounts are the same. And then here, past equivalence, you've added too much silver. And everything that could precipitate has precipitated. And now you're just adding more and more silver. And there's no iodide left to precipitate with it. So I've done the switch. Okay. Here's the really intriguing question. What's on this scale? What's on this axis?
Wait, is it nitrate ions?
No, nitrates should be spectator ions and not be, should not affect this at all.
I was thinking, oh, it's floating around a little bit,
Mhm.
taken.
Yeah, nitrate should just be a spectator.
Then it's concentration of silver iodide. No.
No, can't be. Because that doesn't match where we are. What was it previously?
pH.
pH. So what should it be now?
Wait, is it still pH?
No.
No. Okay, I was like,
Make something up for
We're gonna make something up. All right, let's go back. We've got to put this in a box because it doesn't belong on this page anymore. What does pH mean? It's the negative log to the base 10 of the H plus concentration, which is a measure of how much H plus is there in solution. It's a log scale, which allows these big changes all to be compressed down into usable numbers. Say that again. pH is a value that expresses how much H plus is in solution.
How about is it
P,
P or is it AG?
Eg.
Okay. Oh my god, for real?
For real?
That's funny.
Yeah.
So
It's
we
called
have
so we call that P factor. The guy that invented pH didn't leave good instructions. We just had the 100th anniversary of him writing the paper. pH is about 100 years old. He wrote, I think, in 1922, something like that. And it was a Scandinavian gentleman, and he wrote down, look at this. But he didn't make it clear that P just meant the negative log of something else. So in the absence of clear direction of how to use this number, people have just said that's going to be called the P factor, and the P of anything that follows it is the negative log of that thing. Okay? And we can even make it be of abstract.
Yeah.
Like, why don't you just make that? KAs have these massive variations. why don't you just take the log of the big variation and make it be a usable number? Okay? So we're literally going to plot the concentration of the silver titrated into the solution as a log scale. So instead of being just regular concentration, now we squeeze everything into one.
So, just for like, I guess understanding, so I understand that it's the P of whatever thing, but how do you quickly and find it being like, oh, it's PAG plus that we're measuring, not PI minus? Like, I guess on that graph, how do I know that for sure? Oh, that y-axis is PAG plus and not PI, cause like I is higher. On the
Oh,
one.
hey, you know what? We could do it.
Okay.
Yeah.
Then it'll be inverse.
Mm-hmm.
Yeah.
Mm-hmm.
So.
So this is how logs work. The number for the concentration is expected to be less than 1. And the log of any number less than 1 is a negative number. The negative log in the P factor makes the pH become a positive value. But the trend goes the opposite way, that the more H plus you have, the smaller your value of pH. Okay. As the underlying value goes up, the value of the P factor goes down. And it gets messy when you work at big concentrations, because that's not what it was designed to do.
Okay, so it just goes the opposite way of what you do.
Yeah.
Great.
All right, let's do a titration.
Okay.
We have 25 milliliters of, here's an example. I have 25 milliliters of 0.1000 moles per liter of iodide. And I'm going to titrate against, I think it should probably be the other way around when you say titrate against. 0.00, there's only one zero. That's a mistake. 500 moles per liter. Silver iodide. Okay, this is our reaction. The silver ions and the iodide ions come together to make AgI. That's the opposite of how we would write KSP. KSP represents how much ions can be transmitted into solution if you have a salt that is largely insoluble. And the value of KSP for this is 8.3 times 10 to the negative 17. Okay, so that's what KSP is telling us. Let's use that information what's the value of K for this?
1 over the concentration.
solid. So I get this. Put a value to it.
8.3 times 10 to the
Because KSP is that. This is the opposite direction. So this is 1 over KSP. KSP tells us this is very, very, very far to the left. 10 to the negative 17 tells me there's very little making it into the soluble ions. So when I write my value, when I write my reaction that way, I have the inverse, which is what?
1.2 times 10 to the 16.
Which means this. Very, very far to the right. Okay. All right. Good. Let's do the titration. I've got this much against that much. Let's just jump into, I think we can just jump straight into equivalence. Question. What volume of Ag plus removes all I minus from the solution? Remember, there are only 3 things that we can ever do in a chapter on concentration. They are that moles is mass divided by formula mass, that molarity is moles per liter, and that M1 V1 equals M2 V2. Those 3 things will get us through every question. Sometimes we have to navigate around a bit, but that's all we need. Okay, which one of those 3 things are we going to use? Because what is the question asking for? The question is asking for a volume. So I'm looking for something that uses volume. M1V1 equals M2V2 does use volume. And if I go M1V1 equals M2V2, do I know a molarity that's associated with the volume? And do I know a volume that is missing, but I do know its molarity? Yeah. So V2 equals M1 V1 over V2. Do they need to be in liters?
Not necessarily. Just the same units.
So long as they're both in the same units, they will cancel. So we don't need to be in liters yet. Okay, so 25, well, let's actually do it in the right order. 0.1 times 25, so that's a molarity, 25 milliliters. And as long as my volume down here is also in the same, oh, no, it's, no. I'll get there, I'll get there. I'm looking for the volume, but the volume couldn't have been down there. I'm leaving the molarity down there. 0.05. Those molarities cancel, gives me an answer that is in milliliters.
I got 50
50. How many significant figures am I working with?
You were working with 3.
Yeah, there might be an additional 0 there. What do you think? Because right now that's only 3, isn't it? And I want to use 4. Okay, so 50 milliliters will do it. Let's look at a couple of places on the curve. At equivalence. The amount of silver ions and the amount of iodide ions gets to be the same. And when we think that KSP is the amount of silver ions multiplied by the amount of iodide ions, this is, what did I say, it was 8 point? 8.3 times 10 to the negative 17. That number and that number are the same value. What value are they?
They're half of each other. Well, no. No, they're the same. So you can just make them X.
We don't know what they are, but we know that they're the same as each other. So if I wanted to know how much silver ions are in solution at the point at which what happens is the silver and the iodide meet each other. My equilibrium is really pushed very hard this way. They go ahead and they make every silver ion become a precipitate. And then that precipitate realizes, hold on a minute, I've got a KSP associated with me that gives a tiny amount of it back. It puts a tiny amount of it back into solution. X is the value of the silver ions that are in solution at the equivalence point. They're not all gone, they're almost all gone, which is equal 8.3 times 10 to the negative 7 is equal to x squared. So x is the root of that number, which is what?
9.11 times 10 to the negative 9.
Okay. Now I need to plot that on my titration curve. And my titration curve reads volume of silver against PAG. Are we expecting units for the P? No. P factors have no units. Okay. Here's a follow-on question. This equivalence happens at 50 milliliters.
M1V1 equals M2V2 told us that to make all of the iodide go away, we're going to need 50 milliliters of silver. Okay.
What's in solution when you've only added 10? There's a long way and there's a short way. The short way, got to tell you, requires you to know this new thing. The old way, the long way, the old way just needs you to know that if molarity is moles per liter, then molarity times liter is the number of moles. Make the number of moles match, and your answer just pops out. It's a little bit cumbersome, but it gets there. I'll do both ways.
What do you even know for the new way? What do we know for the new way?
That the concentration of iodide is the fraction remaining multiplied by the original concentration multiplied by its dilution factor.
Okay, I'm
So,
waiting to see that.
Yeah, so that means that you have to know a couple of things that you didn't know before. Okay. At this point, iodide is larger than silver. Yeah. Oh, Pat, you in here?
Hello. I think that you guys are here till 12?
Mm-hmm.
Yeah, we're not here till 12.
Okay.
Just ignore me.
Well, I'm about to run out of time. So the moles of iodide that's swimming around in solution is equal to the number that you started with. Remember, if anything has a 0 in it, that's my initial amount, minus the concentration of the silver that has been added and therefore precipitated. Okay. So, molarity is moles per liter, therefore moles is molarity times liters. These numbers are going to be in liters. Okay. So I'm just going to make this be moles, not concentration. Moles. Yeah.
I was confused for a second.
Yeah. Because I'm going to turn those into moles. All right. I have 0.025 liters. 25 milliliters divided by 1,000. 0.111. That's my iodide, and I'm going to subtract from that 0.01 liters multiplied by 0.05. Okay. That's my silver plus. So this is my 25 milliliters divided by 1,000. This is my 10 milliliters divided by 1,000. There's a number that pops out of this, and it is 0.02 moles of iodide.
Well, that was a long way.
What now?
That was a long way.
Oh, we're not done.
Oh, I was
Not
like.
done. No. That's the moles of iodide. Now, the new volume is the 25 milliliters that you started with plus the 10 milliliters that you added, which is 35 milliliters, which is 0.035 liters. Okay. So the concentration of iodide is moles, and that is liters. That gives you a number in moles per liter. And we'll have to stop. That is 0.0574. Okay? All right, we'll stop there. Here's what we do next, but we're not going to do it. KSP is that number multiplied by that number. We just found that number. We know that number. We're going to find that number. Okay?